Hey, also consider these two cases. There's fluid flowing over a sphere, and the fluid can either flow at a slow speed or it can flow at a fast speed. And in the slow speed, it's this nice laminar flow profile, whereas at a high speed, there's this turbulent regime in the back. And what we want to calculate is, let's say you wanted to calculate the force of drag in both cases. Now, there's no way to characterize the force of drag for this turbulent flow. There's no way to, integrate the Navier-Stokes equations and calculate a drag force. But what you could do is actually run some experiments and actually measure the force of drag in both cases. So you might have some way to measure the fluid flow, the velocity from left to right, and you might know things like the density and the viscosity of the fluid. And in that case, you could just measure the force of drag as a function of these other parameters. What you could do is make a graph of the drag force as a function of velocity. So you'd run the experiment at a low velocity and run it at a high velocity, and presumably you'd get some curve, force of 0 at a low velocity, and you might see some increasing curve like this. And you would do it, and what you would do is, fit a line to these data, or a curve of some sort. And you might do this with a sphere with a diameter of 1 centimeter. And then what you'd want to do, or you might do, is explore, well, what happens if I change it to a 10 centimeter sphere? And you get another curve. So in this case, these data points represent 10 centimeters. And you fit a line to these, and you might well want to do something at 1 millimeter. And here's what the data might look like for a smaller sphere. So presumably you get a bigger sphere, and you'd expect to have a higher drag force. Then what you might be interested in is not the force as a function of velocity, but let's say it's a force. We're looking at a bunch of different fluids, and let's see how the force varies with the viscosity of the fluid. So we'll do an experiment. Let's say you just have a fixed diameter. We're just going to say a 1 centimeter sphere, and we're going to collect data as a function of viscosity. And what you might find, we're going to do it for a couple of different experiments, and what you might find is some trend, and we're going to do these experiments. Here's a velocity of 10 centimeters a second, and you draw a curve. You say, all right, here's the force as a function of velocity. So what happens if I have a higher velocity or a lower velocity at the same diameter? So presumably what we would see is at a small velocity, the drag force would be small again, and you increase the velocity. And if we increase the viscosity, a thicker, more viscous fluid, I would anticipate that the force of drag would be greater. So we get some more experimental data. But note that all of these data points are only for one diameter sphere. In this case, it was 1 centimeter. So we're doing a whole lot of experiments, and we want to figure out, well, all right, what happens if the diameter now is 10 centimeters? Well, in this case, you'd have to go back and measure all of these velocities again using a sphere that was quite a bit, 10 times bigger. And you'd calculate the force in that case as a function of viscosity. So we're doing a whole, a whole slew of experiments just to get the drag force around a simple geometry like a sphere. And then you might say, well, not only is the viscosity significant, what happens if we looked at the force as a function of the density of the fluid? And it's hard to say off the bat what this relationship might be. Does a more denser fluid have a bigger force of drag, a smaller density? And if we look at this now, how does the density compare if we had a given fluid with a certain density and a high viscosity, or a high density and a low viscosity? So you can imagine that you'd have hundreds and hundreds of experiments that you could possibly run to explore the interactions between all these variables. As it turns out, we can combine all of those data based on viscosity, Reynolds number, and diameter of the sphere, and the density of the fluid. We could make a graph of what's known as the coefficient of drag as a function of what's known as the Reynolds number. And both of these are dimensionless parameters. They don't have dimensions like meters or kilograms. There is no dimensions. And we make a plot. The coefficient of drag is equal to the force of drag divided by 1/2 times the area of the sphere times the density times the velocity of the fluid squared. So this area of the sphere is just the cross-sectional area that's exposed to the fluid. So the area in this case, even though it's a sphere, we just care about the cross-sectional area exposed to the fluid, and that area is pi over 4 times the diameter squared. And the Reynolds number is equal to the density of the fluid times the velocity times the diameter of the sphere divided by the viscosity of the fluid. So let's say you did a whole bunch of experiments, and in each experiment you measure the force of drag, and you look at a particular diameter sphere, or a particular cross-sectional area, a particular density of the fluid, and a particular velocity. So if you know all these parameters, you can calculate what's known as the coefficient of drag. And you also calculate, for a given experiment, you know the density of the fluid, its velocity, the diameter of the sphere, and the viscosity of the fluid. You calculate what's known as the Reynolds number. And we make a graph of this, and it turns out for a sphere, what you would observe is some decrease in the coefficient of drag, and in some independent region where the coefficient of drag doesn't change much with the Reynolds number. And then it decreases due to the changes in the fluid flow behavior around the sphere, and then it increases again. So let's say we did that, and we did it, the blue would represent a particular diameter. And then you do this again. Let's increase the diameter. We're going to increase it. We'll double the diameter. So now we're looking at a bigger sphere. And as it turns out, it's a bigger sphere, and the velocity, we're going to vary the velocity, the density of the fluid, different types of fluids. If you graph it this way, what it turns out that these data points fall right on top of each other, or very, very close to one another. And you see this exact same trend, and this might be a smaller sphere, it might be a more viscous fluid, what have you. But you calculate the coefficient of drag and the Reynolds number, and then you do it again, and we'll say, all right, well, here's an even bigger sphere. And in this case, we're going to do it in a very thick fluid. And in this case, it turns out the data points all fall right on top of each other. So what you're able to do is collapse all of these different experiments into a single curve. And what that allows you to do is extrapolate now. Let's say we've got a diameter sphere that we haven't tested. We've tested 1 centimeter, 10 centimeters, 100 centimeters. Well, let's say we had a 50 centimeter diameter sphere and some strange fluid with a different viscosity. And for these dimensions, or these experimental conditions, we can calculate a given Reynolds number. You haven't actually done the experiment yet. You just know the diameter of the sphere, you're interested in the velocity, the density, and the viscosity of the fluid. What you really want to know, what we ultimately want to know, is the force, the drag force on this sphere, this experiment we haven't even run yet. And you calculate, let's say the Reynolds number is in this region. It might be something like 100,000 for this Reynolds number. So I'll draw a line and I'll say the Reynolds number, about equal to 100,000. What that means is, in this case, there's a particular coefficient of drag associated with that, and this coefficient of drag might be something like 0.6. So if you know the velocity, all these other fluid parameters, you can now calculate. You haven't even done the experiment yet, but you can calculate the force of drag.